Alrighty, so section 9.5, transition matrices and recurrence relations. So uh, in this particular exercise, we'll start getting really good uses out of the transition matrices. So let's consider the transition matrix that was used in the previous exercise for the shopping centres. So we had shopping centre E, and basically 75% of customers in a particular week remained to shop at shopping centre E the next week. 25% moved across to shopping centre H. And with shopping centre H, 90% of customers continued to shop at H and 10% moved across to E. So that was our transition diagram that we had. Now let's imagine that in a particular week, initially there are 23,000 shoppers that go to E and 12,000 shoppers that are at H. Then to work out how many shoppers we have at each shopping centre, the following week, we can simply take that initial state matrix, 23,000 at E and 12,000 at H, and pre-multiply it by the transition matrix. So there's our transition matrix in the order of EH, EH. So we put the initial state in order of EH as well. If we do that multiplication, you don't need to do it by hand, you can just do it on your CAS, you'll see that after 1 week, we'll have 18,450 at E and 16,550 at H. So that's after 1 week. But what would happen after another week again? Well, what we do is we take that state and we throw it in here for the next calculation, which is pre-multiplied by that transition matrix, and then you can see the number of customers at E and the number of customers at H. So that state has just been thrown into here. So initially, this here we could think of being the initial state. That's the state after 1 week. This is the state after 2 weeks. And to get that state after 2 weeks, it's just the transition matrix being multiplied by the state after 1 week. So in this way, we've got a repeated calculation continuing on. And this is a really good example of recursion, where we have a repeated calculation. So what we're able to say is that S0, the initial state, was 23,000 at E, 12,000 at H. S of n plus 1, the state for any given number of weeks, is simply the transition matrix multiplied by the state of what it was the week before. So S0 is the initial state matrix, S of n plus 1 is that transition matrix multiplied by Sn, which is the state immediately before S of n plus 1. So as an example, if we want to work out how many shoppers were at each of the shopping centres after 23 weeks, we'd simply have S23 equals T being multiplied by S22. Now we can do this on our CAS. Again, you can see here there's lots of definitions and defining that's required. So you define each of these matrices and then call them up. I strongly encourage you not to do that. I encourage you to use copy and paste instead. I think it just makes things a lot easier. Now, what we're going to do is come up with a general rule for this, and this will be the most useful part of transition matrices. So if we've got the initial state and we define that as being S0, then S1 is going to be the transition multiplied by what it was previously. So S0 in this case. So S1, we've got S0. S2 is going to be the transition multiplied by the status immediately before S2, which is S1. Now, given S1 is defined as being T times S0, then really we can say it's this T being multiplied by S1, which is also equal to T times S0. So we can say it's T squared times S0. S3 is going to be the transition multiplied by the state immediately before S3, which is S2. And so it's that transition matrix. And then that's multiplied by what S2 is equal to, which is here. So that's T squared times S0. So obviously T cubed times S0. and then that pattern continues on. So basically what we see here is that if you've got any nth status, so Sn, then it's t to the power of n multiplied by S naught, where S naught is the initial state. Now the key to this is that basically if you're after Sn here, then the power of the transition matrix and the state down below here, so in this case naught, need to add up to that figure. And that's shown in this example. So if we're after Sx, then it's going to be the addition of those two need to also happen. So if we've been given S0, then we need to put t to the power of 4. So we get that S4. Same example, if we're after the fourth state, then and we've been given S1, then we need to use the transition matrix raised to the power 3. So you can see that the 3 and the 1 give us 4, the 4 and the 0 give us 4 as well. And you'll see that more clearly with a couple of these examples that follow. So here we've got ourselves a fleet of trucks, and they start themselves at either of these two depots, depot A or B. So at the start of the day, they're either at A or B. Now 95% of the trucks that start at A will start the next day at A as well. And 5% will start at B. If we consider depot B, 85% of the trucks that start at B will start at B the next day. 15% will start from A. So that's our transition matrix. Now at the start of a particular day, there are 40 trucks at A and 100 trucks at B. So our initial state, S0, is 40 at A and 100 at B. Notice we've got the order AB, AB, and the same thing here with the initial state, AB. Don't mess that up. How many trucks will be at each depot after 6 days? So S6, the status after 6 days, is going to be the initial state matrix. So that's that S0 there, being pre-multiplied by the transition matrix to the power of 6. So notice that we're after S6 and that these two figures here need to add up to 6. And given that we've got S0 there, then it's obviously going to be the transition matrix raised to the power of 6. So I throw in my transition matrix to the power of 6 multiplied by S0, and I spit out 88 and 52. So 88 trucks will start at A and 52 will start at B. Notice that there are a couple of squiggly lines that just means approximately equal, so you round it to the nearest whole in these examples. B, how many trucks are there in at each of the depots after 10 days? So this time we're after S10. And I've got my S0 that's been given to us, so 40 and 100. And obviously I'm going to get the transition matrix and raise it to the power of 10 because that figure and that figure need to add to get this. So that's why it's t to the power of 10. And you can see that there are 98 trucks that start at depot A and 42 trucks that will start at depot B. The transition matrix can be really useful in determining long-term trends. So let's look at this first example here where we've got from A to B and moving across from A to B. So the 0.6 represents that 60% of whatever it is that starts at A will continue to be at A. And 40% that were at A will move across to B. And this 1 represents that 100% of whatever comes to B will remain to be at B. So what we can clearly see here is that eventually all of the population or all of the trucks will end up at B because of the A, 40% move across to B, but once they get to B, they're always going to stay at B. There is no percentage at all that were at B that move across to A. So eventually, over time, all of the trucks in this particular example are going to end up at B because we've got a 0 here. Now the key to looking at long-term trends is to consider this diagonal. Remember this diagonal here, this leading diagonal, represents 6% going from A to continue at A and 30% starting at B, continue to remain at B. So if we look at this particular diagonal, the point 4 represents of those that were at A for a particular week or day, 40% will move across to B. And the point 7 represents that 70% of those that were at B will move across to A. So what we're considering is the moving across part. So 70% moving across to A, 40% of A moving across to B. And we just compare those two and say which one's the larger. So obviously the 0.7 is larger, and that represents B moving to A. So long term, what's going to happen here is that we'll end up with more at A than at B. The reason being because out of those two across this diagonal, this 0.7 is larger than 0.4, and that represents movement to A. So therefore we say that long term we're going to end up with more at A. And that's explained in the notes, and it's also more theoretically explained here as the A11, A12, A21, A22, and so on. But I'll just leave it with that explanation. Just want to talk about the steady state matrix, and it's sometimes referred to as the equilibrium state. In lots of cases, what will happen is that the status will reach what they call a steady state. So what will happen is that after so many transitions, there will be no change to the status. That is that the values at each of the points won't change at all. And we refer to it as this. S of infinity, which just means a steady state, is equal to the transition matrix raised to a power of 100 times S naught. And just to verify that there is no change in the state, we just do t to 100 times S naught, get the values, and we also do t to the power of 101, so one more, times S naught, get the values. And what you should see there is that there are no change at all in the values that you get. So we'll have exactly the same figures for each of the positions. So the steady state will be achieved if either of these conditions are true. So if there are no zeros in the initial, in the transition matrix, so if there are no zeros in the transition matrix, then we'll be able to obtain the steady state. And also, if we do have zeros in the initial transition, if we then take the square of that, so t squared, if there are no zeros in that particular matrix, then we'll also have a steady state solution being possible. Okay, but if you have a zero in the initial T matrix and then you square it and you still have a zero, then you are unable to obtain the steady state, and therefore it will not have a solution. But if you have T squared with no zeros, or you have T with no zeros, then you are able to apply T to 100 times S naught and T to the power of 101 times S naught to obtain the steady state. So T to 100 times S naught will give us the steady state, and then if you do T to the power of 101 times S naught, that will just prove that your steady state has been obtained, and it will verify that there is no change regardless of what the power is. Let's look at this as an example to make things a bit clearer. So at the start of the day, there are 40 trucks in depot A and 100 trucks in depot B. So this is our transition matrix. Depot AB from 2. In the long term, which depot will have the more trucks? So we are comparing this diagonal here. So this is 0.05 representing change from A to B, and 0.15 representing change from B to A. So comparing those two, the 0.15 is larger. That represents change from B to A. So the A will be larger. There will be more at A. So long term, there'll be more trucks in depot A. Formally written, the 0.15 is greater than 0.05. That is the position A12. So A12, 0.15, is greater than position A21. Therefore, there'll be more at A. And that's defined in the rules. But the easiest way, just looking at that diagonal, which is the larger of the two, this one, that represents change to A. Therefore, A will have more. how do we know there will be an equilibrium state solution? So how do we know there will be a steady state? So in other words, how do we know that eventually there will be a certain number of trucks at A and a certain number of trucks at B, and regardless of how many transitions we do after that, it'll still be those same figures. And what we do there is we just look at the initial T matrix. There are no zeros in this T matrix, therefore we know that we will be able to obtain what we call the steady state or equilibrium state. If there were zeros for that, then we'll take that matrix, raise it to the power of 2 and see if that had zeros. If that didn't have zeros, then we'd know that we'd also be able to get the steady state. C asks us how many trucks are in each depot after 29 days. So we want S of 29. We've been given S0, so we need to get the T matrix and raise it to the power of 29. So 29 and 0, up to that 29 there. And you can see we end up with 105 and 35. And now we need to do it for after 30 days. So we do S30, and we've got T to the power of 30 times S0, and we come up with the same status. Alright, use your answers to estimate the steady state matrix or the equilibrium state matrix. And what is the long-term trend? So the estimate for this, remember we've got approximately equals here, is it'll be 105 starting at A and 35 starting at B. Now we could also do that without being guided and doing 29 days and 30 days. We could just do straight away S of infinity equals T to the power of 100 times S0, and it will achieve that matrix. And then verify that we've reached a steady state by doing the next status across. So we would have T to the power of 101 times S0, and that would also produce the same.